Yeah, let's continue the EDTA titration. Okay, as I very strongly emphasized, the important part of the EDTA titration, although it is not shown in the textbook, this equation, okay, metal ions, okay, make a one-to-one complex. Yeah, it is quite well known, but important is that any forms of EDTA can be used. For example, now is uh, well di protonated EDTA form Y2 H2 Y2 minus. It also can have a complex with metal ions. Okay, to form this one poorly protonated metal EDTA complex. As a result, protons are liberated, so the solution pH will be lowered. Okay, this part is important, but I don't know why the textbook, any textbook, I don't find any explanation like this. Okay, so in other words, in scientific term, protons and metal ions are competing for the complexing site of EDTA, and all the time, most all the time, metal ions win. Okay, uh, almost all the time, but at a very low pH, very acidic conditions, this reaction um, does not occur anymore. Okay, we'll we'll visit that part here. The conditional formation constant. Okay, well, actually, the EDTA and metal ion, the formation constant Kf is so high. Okay, very high. So solving a problem is no problem. But in order to develop the theory, we have to consider in more detail. Okay? Usually, EDTA titration, EDTA uh, work is done at constant pH. Okay? Yeah, usually, yeah, that's the usual practice. Since the pH changes as metal ions added to the EDTA solution, yeah, as I as you saw, usually pH of the solution is made constant, okay, by using a buffer. Okay. In that case, we can develop, further the EDTA theory. Let's see. Let's start from this equation. All right. The important part is the polluted protonated form. That's the concentration is given by the total EDTA concentration. Now it is represented by this parenthesis EDTA, okay, and multiplied by this a fraction, okay, of y4 minus at that pH, okay, alpha y4 minus, okay. Okay, now let's rewrite the formation constant using this equation. Okay, and then instead of this y4 minus concentration, we use this one. Okay, and now this when the pH is fixed, alpha value is also fixed. Okay, now let's move this alpha to the left hand side, this one, and then we redefine, okay, this one as Kf prime, and we call it conditional formation constant. Conditional. Why? The pH is fixed. Okay? It is given by this one. But don't forget, this EDTA, right? This concentration is the total concentration of EDTA species, which is a seven exists in 7 forms, not bound to the metal ion. Okay, not bound. Okay? Metal bound EDTA concentration is given here in the numerator. Okay? So from now on, we can write at a constant pH, we can write this reaction, okay, here, and then uh, the equilibrium constant for this equation is Kf prime, yeah, conditional formation constant. Okay, let's take an example. Using a conditional formation constant, calculate the free calcium ion concentration. Okay? And this one, Kf formation constant for calcium ion with EDTA is 10 to 10.65, very high. Okay, and then now the pH is 10 and 6. All right. Well, let's write the EDTA reaction this way, and then conditional formation constant is given by this one, and then alpha values are known at each pH. Okay, pH 10, and what is alpha value? From the table, you find 0.30. Okay, and then at pH 10, okay, conditional formation constant is 1.34 times 10 to 10. Okay, smaller than this one, and at a lower pH at 6, Kf prime is this one. This is quite low at the low pH. And still, Kf prime is 8.0 times 10 to 5. This is still a very high number, a large number. Yeah, that's because original formation constant is really large. Okay, that's why even at pH 6, it is possible to determine this calcium ion concentration with EDTA. Okay, let's calculate. What is the our target? Okay, the free calcium ion concentration. As usual, we write this way, and then initially there is no calcium ion. All right, and only this one. The condition is calcium EDTA complex, is 0.1 molar. Okay, we start from here, and it's dissociates. I mean the reverse reaction takes place, although little. Okay, and we put X and X, and then we apply this equilibrium constant and X. This one after dissociation, this concentration a little bit lowered by X amount. Okay, so we write the equilibrium equation, and then we can solve this one. This is just a quadratic equation, and exactly solved. And then at pH 10, calcium free calcium ion. This is free one, free calcium ion, and this one, the numerator, this is not free calcium but bound calcium ion. Okay, and we calculate calcium ion concentration at pH 10 is 2.7 times 10 to minus 6 molar. Okay, and at pH 6, calcium ion concentration becomes lower, becomes higher, because more calcium ion is delivered, dissociated from this complex, which is 3.5 times 10 to minus 4 molar. Okay, at higher pH, complex is less soluble, becomes more stable. Why? Because the alpha values, alpha Y4 minus values becomes more and more larger and larger at high pH. At low pH, alpha values are very they rapidly become smaller, right? That's why it is important to fix the pH, in order for you to do the titration. At so there is a limitation in pH for each metal ions. Okay, but and when the formation constant is larger, as the escape becomes larger, and then the pH limit becomes lower, lower and lower. All right? Yeah. I hope you fully understand. All right, let's see in more detail the pH effect on EDTA complexation here. Yeah, this figure shows very well, and depending on pH. Okay, this is a cobalt divalent cobalt titration with EDTA as a function of pH. As you see, at higher pH, the result is the best one, and as pH is lower and lower, and then you see in pH 6 it is not easy to find um, the the end point, right? Equivalence point at pH 5. Yeah, it's almost impossible to find. Oh, where is the end point, right? Okay, yeah, and okay, let's stop the temporal here, right?